So today we're going to start looking at Chapter 6. Okay, so Chapter 6 starts trigonometry. So what I like to do first, and when I do Intro to Trig, which is a half-year class for seniors, we just kind of go through like look at the words, you can figure out what it means, and then I'll show you guys a few examples of stuff you can do with trig. So if you kind of break that word down, does anybody notice like a prefix or a suffix or something in there that they know the meaning of? Any?
Metri means measure.
Yeah, so metri is measurement or measure. And there's different subjects that end in metri. So there's trigonometry, geometry. I guess that's probably it. But there's at least a couple that end in metri that I can think of. What else? So measuring something. Yeah?
Tri means 3.
So tri means 3, and I'm even going to extend it a little bit further to a trigon, which is the name of a shape. Does anyone know what shape that is? Trigon? It's a triangle. There's a name for every polygon that ends in gon. Some are more common than others, like hexagon, octagon, pentagon. You probably have heard of those. Four-sided shape is a tetragon. Normally we call it a quadrilateral, but you can call it a tetragon. And a three-sided shape is a triangle, but you can also call it a trigon. So basically, triangle measurement. All right, so a lot of what we do in trig is going to involve somehow making a triangle and looking at sides and angles. So, for example, let's say you had, right here, this will represent land. Out here is water, and there's a boat out there. And we've got 2 Coast Guard stations. Maybe one here and one over here. Okay, and that boat, maybe it's at night, and that boat is maybe their GPS isn't working and it's cloudy, so they can't see the stars, and their GPS isn't working, so they don't know exactly where they are. And it's nighttime, so they can't see very far. Well, they've got a light on top of their boat. Okay, so maybe they radio one of the Coast Guard stations and try to figure out, can you tell me where I am, because I lost my navigation. And the Coast Guard station may say, yeah, just turn on a light. Turn on a light, maybe it rotates on top of the boat. So what that allows the Coast Guard station to do is spot the boat. They can see it. And this station might see the light on top of the boat. And if one station saw it, all that the station could say is, well, from my position, your heading is 120 degrees in a northeast or whatever direction. But the problem is this station wouldn't be able to say how far away. They would only be able to say, basically, you're on a line between me and this compass heading. But I don't know if you're 5 miles from me or 10 or 15 miles. I can't tell. So that's where another station would come in. If that station can see the same light on the boat, that station can say, well, all right, I see the light at this heading. This station says, okay, I can see it at this heading. And the 2 stations communicate. And they would know how far apart they are from each other. Because the stations are probably marked on a map, or the location of each station is known. So this distance from here to here would be known. Okay, maybe it's, I don't know, maybe they're 25 miles apart. Knowing how far apart the 2 stations are, and knowing the heading that each station can see the light at, we can make a triangle out of that. And the headings are going to give us some angles. Using those angles and that distance, we can figure out exactly where the boat is. And then guide them wherever they need to go. From there, once the boat knows where they are and they have a fix on their position, then they can use a compass and they can continue in monitoring their speed and their direction, and then they can figure out where to go from there. They just need to know where they are now, and then they can figure out where they'll be if they travel at a certain speed. So that's one thing we can do with trig. Let's see, what else can we do? You could do the same kind of thing with like cell phone towers in a cell phone. If you call, I'm pretty sure most cell phones now, if you call 911, the GPS pretty much turns on automatically. And as long as either if that doesn't turn on, as long as you're in range of cell phone towers, which if you're making a phone call, you must be, the cell phone tower can kind of pinpoint where you are, especially if you're in range of a couple. So if you're just in range of one tower, that's probably not good enough, because then they could figure out like a circle. You're somewhere near that tower, maybe within 5 miles. But if you're in range of like 4, 5, 6 towers, they can say, well, there's a very small area that that person could be if they're connected to the 6 different towers. So somebody that was in like a car accident or something, they can triangulate roughly that person's position. If their phone has GPS, they can figure it out pretty much exact, within like a few feet, usually. But you can triangulate. That's how GPS works. You can triangulate your position. A little more complicated with GPS because you also have 3D. So not only do you have, like if you're flying a plane, you have to know like your latitude and longitude, but then you also have an elevation above the earth or on the earth. Makes a difference. So that's a few different things we can do with trig. We can also, what else can we do? One other thing I can think of. You could, for example, if I was outside, I could find the height of an object in front of me. Any object. As long as I had a couple instruments to measure. Like maybe I had a tree and I had to cut it down and I knew it was going to fall a certain way. I could figure out, okay, what's the height of the tree without climbing it. Just get the height of the tree and then say, okay, it's about 200 feet from the house. So as long as the tree is only 200 feet, it should be okay when it falls. No matter which way it falls, it won't hit anything. But you can figure out heights of buildings, any object that you can see, you can find the height of it in front of you. If you know how far away you are from the object, it's a little easier. If you don't know how far away it is, you can still do it. So like if there was like a mountain, maybe way in the distance, or like maybe you're in the desert and you see an object like flat so you can see, that's why I said desert. And you see an object in front of you and you're like, I wonder how tall it is. Well, if it's like 3 miles away, you might not know that. You don't know how far away it is from you. Unless you had like a car and you could drive up to it and then look at your mileage and then drive back. But you don't even need to do that. You can figure out stuff. It gets more complicated though using trig like that. Right, so we'll do some stuff that's more like real world where I can definitely give you an example. Also because it's pre-calculus, we do a lot of stuff that's theoretical, like more simplifying like trig identities. Right? Not as much of a real world application for that until you get to calculus. Right? But we'll talk about stuff like that. All right, so first thing we're going to look at in trig is basically angles and how we measure them. Okay, there's 2 main ways that you can measure an angle. Does anybody know, I think I said it earlier, but anyone know the 2 ways that you can measure angles, the units we use? Yeah.
Degrees and radians.
Yeah, we can use degrees and we can use radians. We haven't touched the setting all year on the calculator, but there is a setting for it. Under mode, we have radians and degrees. Okay, we'll be using that a lot when we use the calculator. So, before we can measure angles, I'm just going to kind of a little bit of geometry background, make sure people remember like what an angle is and stuff like that. So basically an angle is made up of 2 rays with a common starting point. Does anyone remember what that starting point is called?
Vertex.
It's the vertex. Yep. So basically an angle is something that looks like this. If you're going to draw an angle all by itself, not part of a shape, that's how you would draw it. 2 rays. Now, technically, if I were to draw a triangle, like that, the sides of that triangle are not rays. What are the sides here? They're line segments. And technically, that, and that are angles. Even though it's not made up of 2 rays, it's made up of 2 line segments. That's okay. So if you draw an angle all by itself, you do rays. If you draw it in a polygon, it's usually made up of line segments. Now, in this picture right here, we've got 2 sides to the angle. Okay. One side is the initial. One side is the terminal. So the way we can basically figure out which side is which, if you're given just two rays, it's kind of the direction of rotation. Right? If you go inside the rays, put yourself inside, as you rotate counterclockwise, wherever you end up, that's the terminal side. Where you start is the initial side. So like if I drew an angle like this, I go in between the two rays, and I go counterclockwise from one ray to the next. In between, counterclockwise from one to the next. This is the terminal. This is the initial. What we normally like to do is when we draw an angle, we always put the initial side horizontal. Drawing it like this in red, it's almost like it's kind of been turned. We normally don't do that. We do it more like the one in black. Now, I wrote we really have two angles here because you have the one inside and the one outside. This is the one outside. Most of the time, we're talking about the angle between the rays. Okay? In other words, the angle that is less than 180. Okay? Not the angle that's on the outside. Okay. So any question on how to figure out for an angle which side is initial and which side is terminal? Okay. How about if I drew something like this? So I got a 90-degree angle. Which side is initial there? The horizontal. In between the rays, okay. Rotate in a counterclockwise direction. Initial, terminal. Again, that would be kind of a weird way to draw a 90. If we're going to sketch a 90, this is how we'll normally do it. Try to put the initial side on the x-axis, horizontal. Okay, so when we go through trig, a lot of times we're trying to solve for an angle. Well, in algebra, when we solve for something, x and y are used a lot. We'll use x and y too. But most of the time when we're trying to solve for an angle, we're going to use a Greek letter. That's just how we normally do it. So I just want to make sure I didn't skip anything. So these are just some of the Greek letters that we're going to use. We're definitely not going to use all of them right away. But does anybody know any of these Greek letters, if we starting from left to right?
Alpha, beta, gamma, theta. I don't know the last name.
Yeah, so alpha, beta, gamma, theta. The last one is omega.
Oh, cool.
Now, if you're in some trades, you might have seen this symbol before, like in electrical. That means resistance, and that is also called omega. Well, that's capital. The ones in black are lowercase letters. There are capital versions of these letters as well. We generally don't use the capitals. We stick with the lowercase. Okay. And again, a Greek letter is usually used to represent an unknown angle, not a side. Sides, we use the same letters you use in Pythagorean theorem, ABC, pretty much all the time. So, I told you guys that when we sketch angles, there's kind of a standard way we always do it. And the normal way to draw it is what's called standard position. Two things have to happen if I ask you to sketch an angle in standard position. One, the vertex has to be at the origin. Two, the initial side is on the positive x-axis. By drawing an angle like that, standard position, it takes the guesswork out of which side would be initial and terminal. I mean, it's not that hard to figure out. But now, it's even easier. Okay. So that angle in red is standard position. Okay. How about if I did this? Is that standard position?
No.
No, what's wrong with it?
It's not in vertex.
Right. Initial side is good, still on the positive x-axis, but the vertex is no longer at the origin. How about if I did something like that? No, what's wrong now? Right. The initial side is not on the positive x-axis. The terminal side is on the y-axis, but that doesn't matter at all. Initial side has to be on the x, vertex at the origin. Okay, so that's called standard position. Questions on that?
No.
So degrees is probably the way that I think most people are familiar with measuring angles. If you take calculus next year, you don't use degrees at all. Right? Degrees, they make some things in calculus more complicated. So they use a different way to measure, and I'm going to show you guys what that is. But we'll talk a little bit about degrees first, and we use both in this class, pretty interchangeably, degrees and radians. Does anybody know, like in a full rotation, like around a circle, how many degrees that is? 360. So a complete rotation in the counterclockwise direction is 360. The reason I say counterclockwise is because there's two directions you can move on a circle. You've got clockwise and counterclockwise. Which way you go makes a difference. I'll talk more about it. Okay. How about a half revolution? Quarter? 90. So these are angles that come up a lot. Any angle that's a multiple of 30 or 45, and there's some overlap there, but 30s and 45s are the most common angles we will use in trig. Once we get to like unit circle, that's pretty much what the unit circle is all about, angles that are 30s and 45s. That's something that we'll pretty much memorize, so by the time we're done with it, I would be able to ask you a question about a 30 or 45, and you'd pretty much know off the top of your head. There are other angles that come up, but not as important as those. Okay. So, I told you that there's two directions you can move when you're measuring an angle. If you measure in a counterclockwise direction, that's positive. So what do you think would happen if you measure clockwise? Negative. Yes. Okay, so what I'm going to do now, I'm going to show you a program that I have that just lets you draw different angles. And every angle that I'm about to draw is going to be in standard position. The vertex will never leave the origin, and the initial side will never leave the positive x-axis. So what I can do is grab this little circle and position it wherever I want. Okay? So I can basically take the terminal side and just move it around the circle. Okay. So as I move it around, I'm going in a counterclockwise direction. Notice that the angle is getting bigger, okay? 219 degrees. There's also another number below. Anyone have a guess what that one is?
Radian.
That's the radian. You might notice that if I drag it to certain spots, all of a sudden you see a pi. Well, you're going to probably see pi come up when the angle is a multiple of 30, 45, and this one might even do some of the like 22.5, which is half of 45. It might do some of the ones that are in the halves too. But definitely, anything that's a multiple of 30, you're going to see pi come up. When it's not a multiple, it rounds it off. Okay? And that's pretty standard. So like 300, probably going to see pi come up there. Yep. If I keep going, all that happens now is I've gone around more than one revolution. So now that's 372 degrees. So that's one full revolution and then 12 more degrees. Okay. If I go the other way, now I have negative angles. So it'd be nice if there was a little arrow on this red arc showing you the direction, but it's measuring in a clockwise direction. So basically, if you've got, let's say, something like this, just try to get it at 90. Focus on where that red circle is right now, okay? Compared to where it is now. What's the difference between where it is now and where it was before?
It treats it like it's like on the y-axis because it would have run like the opposite way. So
Well, pretend you can't see anything else on the screen except that little red circle. All you can see is that area that my hand is over right now. Didn't change. If that's all you could see, that area would look exactly the same. And in trig, negative 270 and positive 90, whenever we're doing trig stuff, is the same thing. So given the choice of working with either negative 270 or positive 90, I would go with positive 90. It's easier. Now this program is also rounding a little bit. That's why it still says it's the same. Once you move enough, it changes. But 90 is pi over 2, not 91. Just the way it rounds. I already mentioned that to you. So angles can be larger than 360 degrees if they make more than one revolution. Generally, though, we don't want to work with angles that are larger than 360, especially when we get into unit circle trig. If you have an angle that's larger than 360, you want to make it smaller. And we'll talk about what you can add or subtract to make an angle larger or smaller without affecting the answer, okay? But just giving you something easier to work with. Anybody think they know? I just showed you that negative 90 and 270 were the same. Anyone think they could tell me the arithmetic to get from one to the other?
Can you just like add 2 pi to the top, which is like a full revolution?
In radians, I would have added 2 pi, which in degrees, what do you think that is? 360. Anytime you add or subtract one full revolution, it brings you exactly back to where you started. 450 is another angle that's the same as 90. It lands in exactly the same spot. So if I was given an angle of 450 and I had to do trig, I'd say, no, I'm just going to use 90. It's a smaller number. It's easier to work with. It's even easier if like somebody gave me an angle like this. So if you gave me that angle off the top of your head, 3,690, I would not know off the top of my head that that's 90-degree angle. Because you've gone around so many times and you've made it so big, it's hard for me to think about it when it's that big. Right? So I would say, well, I'm going to make it smaller, basically by subtracting 360 as many times as I need to, till I get it back to exactly the same spot. But now I've got a smaller number. Okay? So we'll talk about that too. So the fancy name for those angles that I just showed you is called coterminal. Yeah.
Well, it was about the unit circle. Like, how would you, without using that, like, app that you're using, how would you know?
Where it is?
Yeah.
I would just add or subtract 360.
So you would just keep doing, like, subtracting 360 until it's a very small number?
Yeah. Specifically, a small number between 0 and 360.
Right.
Because if you subtract 360 too many times, now you're going to go negative. You don't want that either.
Okay.
So all these angles that I just showed you, negative, what did I do? Negative 270, 90, 450. Those are what we call coterminal angles. Coterminal angles have the same initial and terminal sides. Okay. There's 90. There's 450. Exactly the same initial and terminal sides. So those are called coterminal. To find angles that are coterminal with another angle, add or subtract 360 as many times as you need to. So what we're going to do, we're just going to make a quick sketch, and then I'm going to give you an angle, and I want to find an angle that is coterminal with the angle that I give you. One positive, 1 negative. So remember, add or subtract 360 as many times as you need to. So let's look at 30 degrees. All right, so 30, I'm picking that one because it's an angle that's going to come up a lot. And I want to sketch that first. And it said to sketch it in standard position, which means the initial side is where? On the positive x-axis. So no question, that's right there. Now, I'm not looking for it to be exact, but if you think about 30 degrees in terms of quadrant 1, how far of the way through quadrant 1 are we?
1/3.
1/3. If you were straight up, it would be 90. Halfway is 45. So just make it look less than half. Now, I want to know an angle that's coterminal with 30 degrees and positive. 390, yep. And how about an angle that's coterminal and negative? Negative 330. I would really prefer to work with either one of those angles. Given the choice, I think that's the simplest one. So, but if you were given one of these on a test, you could change it into that one when we start doing trig and typing stuff in like sine and cosine. And just, this won't really mean a lot right now, but I'll type in, let's go into degrees first, just to show you. Let's take the cosine of 30. You get that number. Let's take the cosine of 390. It's the same thing. 30 and 390 doesn't matter. Same exact thing. So given the choice, I would prefer to work with the 30. If I'm going to get the same answer anyway, I'll work with the smaller number. Okay, let's do 145. Okay, so if I went halfway around, how much is that? That's 180. So it's not quite halfway. This would be 90. This is 180. Where's 145?
Just over half.
A little over half. Half would be 135. So if you go half, go a little bit more than half. I don't know if that looks a little more than half, maybe. And there's 145. Okay. Now we'll do same thing I just did. I was trying to do that. Okay. What's an angle that is coterminal with 145 and positive? 5, how much? 505. And how, just in case somebody's not sure how we got that, what did you do? What was the math? Just add 360. Okay. We'll do this one out together. 145 minus 360.
I might have to stay after for extra help.
Negative 215. Okay. Questions on that?
Guys, getting past the second go back into digital.
Okay, and let's try this one, negative 45. Okay. Initial. Now, because it's negative, what does that mean in terms of my rotation to get to the terminal side? It's clockwise. How many degrees? It's clockwise 45 degrees. Okay. Negative means clockwise. In terms of a quadrant, where is a 45? It's in the middle. Okay, it splits the quadrant right in half. If you want to draw that in, you can to show the direction. Okay, so negative 45. That's not an angle that I would choose to work with. I always like to work with a positive angle if I can. Doesn't make a huge difference. But what's an angle that's coterminal and positive?
315.
315. How about an angle that's coterminal and even more negative? Negative 405. Okay, so any questions on finding angles that are coterminal with a given angle?
And then if you added 360 to 315, that would also be coterminal?
Yes. Any of these are coterminal with the original angle. You can just keep adding 360. Okay. But I think the best version of the angle to use is the one between 0 and 360. That way it's not too big and it's not negative. All right, so we're going to write down a few definitions of some terms having to do with angles. In the definitions, I'm going to use theta, just going to represent an angle, any angle. What does it mean if an angle is acute?
Less than 90 degrees.
Yes,
But greater than 0.
but greater than 0. So for example, negative 10 is not acute. It has to be between 0 and 90. Okay. So acute angles, it's going to come up all the time when we start doing right triangle trick. Sokotoa, that kind of stuff. Opposite adjacent hypotenuse. We'll see lots of that. How about if an angle was exactly 90? What's that?
Right.
Right angle. That's where you have an angle equal to 90. How about an angle, well actually I'll just give you the name. What's an obtuse angle? Between 90 and 180. Yep. I think we don't use this term a lot, but when you go more than 180, I believe it's called a reflex angle. So when you go more than 180, I'm not sure if there's an upper limit on that, like more than 180, but less than 360. But if you look reflex angle up, it'll say something about the angle being bigger than 180. But we don't really use that term much. So all of these definitions apply to a single angle, okay? Just one angle. This definition, next one, applies to a pair. You're gonna have two. Anyone remember what complementary angles are?
Isn't it two angles equal to 90 degrees, or is that the
Two
one?
angles that are both equal to 90?
No, two angles added together that equals 90, or
Okay.
two adjacent angles.
How about negative 10 and 100? Those are two angles that add together that would give me 90.
So positive angle.
Yes. They both have to be positive. Two, or I guess you could say two acute angles, because if you said acute, that also means positive. But two positive angles that add up to 90.
What's the term for the negative angles? Or is there not one?
I'm not familiar with any term for negative angles. Yeah. And what's the other term that you usually study?
Supplementary.
Supplementary, and what's that?
20.
Two positive angles that add up to 180. Now, what are the different kinds of angles you could have that add up to 180? If you think in terms of like acute and obtuse and right angles. Could you have two acute angles that add up to 180?
No.
No, those would add up to best case 179.9 repeating. Right? Because you can only go up, you can't go up to 90 with acute. Could you have two obtuse angles that add up to 90? No, that wouldn't work. Could you have an acute and an obtuse? Yeah? What else could you have?
Two right.
Two rights, and that's pretty much it. So the only two cases you could have for supplementary is an acute and an obtuse, or two right. Okay. Negative angles do not have complements or supplements. So like if I asked you what's the complement of 40, I'm asking you what do you add to 40 to get 90. That's what that means. Negative angles, there is no answer. Okay. So I'm going to give you some angles, and I just want to know the complement and the supplement. Okay, so 48 degrees. What's the complement? 42. degrees. And the supplement?
32.
90 plus 42 is 132. Okay, complement, supplement. So in the homework, it might seem like there's kind of a lot of questions, but a lot of them they're very quick. Like add 360, minus 360, find the complement, find the supplement. They're not very long problems. What's the complement of negative 18?
Doesn't have one.
Supplement?
Doesn't have one.
Yeah. Doesn't apply. There are no complements or supplements for negatives. Now here, assume x is acute. X is acute because if x was like 140 degrees, it wouldn't have a supplement or a complement. It's too big. So assume that it is acute. What would be the complement of x degrees? Yeah.
90 minus x.
Again, assuming x is acute. And what would be the supplement? 180 minus x degrees. Okay, so any questions on finding complements and supplements? Okay. So, another way to measure an angle is radians. So we'll be using radians a lot. Now, if you look at the word radian, does anybody see another word? It's almost like the beginning of it. It's almost like another word, Zach.
Rad. The radicals.
Okay, like rad is in radicals. This won't have a ton to do with radicals, but that's definitely a good guess. Another word, even using a few more of the letters. Yeah.
Radi, like radius?
Yeah, R-A-D-I. And then we don't have US, we have A-N-S. But it's almost like the word radius. And there's a connection between a radius and a radian. Okay, and I'm going to show you that eventually. So let's start with this picture. So what I've drawn here is it's called a central angle. It's a circle. Inside, at the center of the circle, I put a vertex with the angle. The angle has two rays, CA, CB. Ray CA intercepts the circumference right there. Ray CB intercepts it right there. If you connect point A to point B, you get an arc. That's called the intercepted arc AB. Or in geometry, we can write an arc as two letters with a curve over the two letters. Okay? That's called a central angle. So it's an angle in a circle. Now, I want to look at kind of something special that could happen here. Let's say that you took a ruler and you measured the length of this. You get a number. Okay? That's the radius of the circle. Now, let's say you took a piece of string, you put it on point A, you put it exactly on top of that arc, and you stopped it at point B. So now you've got an arc. Then you took that piece of string, you straightened it out, measured it on a ruler, and let's say that it happened to come out exactly the same. That won't always happen. Most of the time it doesn't. The arc could come out bigger or it could come out smaller. But if it did come out the same, then what you have right here is an angle that is 1 radian. So angle ACB would be exactly 1 radian if the size of this arc matched the size of the radius. So what I'm showing you is I'm just trying to show you a connection between the word radius and radian. Still doesn't explain how do you convert from degrees to radians. Doesn't answer that question at all. Doesn't tell you how many degrees are in a radian, anything like that. But if you sketch a picture and that arc is exactly the same size as the radius. You just drew a picture of one radian. Any question on that? What would happen if arc AB was smaller than the radius? What do you think that would mean about this angle?
It would be on less than radian.
It would be less than 1 radian. That might look something like this. That arc is very small compared to the radius. That's an angle smaller than 1 radian. What if that arc was bigger than the radius? Then you'd have an angle that's more than 1 radian. If the arc is exactly equal to the radius, then it's exactly 1 radian.
So what is a radian again?
A radian is a unit of measure for an angle.
Oh.
It's kind of like asking, what is a degree?
Oh.
It's a unit of measure for an angle. And I'm trying to show you visually what 1 radian would look like. Okay. That's not exactly to scale. It'd probably be a little bit smaller than that.
Okay.
It's close, but I think the arc is a little too big there to be drawn to scale. That's another thing. Nothing that I draw in trig is to scale. So, converting between radians and degrees. Okay, we said this earlier, but 1 full revolution in degrees is how much?
360.
360. So, what I basically have to do to figure out how to convert between degrees and radians is I have to get some kind of fact to start with. For example, if I wanted to convert between feet and inches, I wanted to set up a formula. What's a fact that you know about feet to inches? 12 inches in 1 foot. If you tell me that, as long as it's true, I can use it to figure out anything I want. Like, if 12 inches is to 1 foot, 90 inches is to how many feet? The key is I just needed something to start with. Okay? That's basically what we have to figure out here. If you can figure out one connection between degrees and radians, just one thing that's true, like this fact right here, then you can figure out anything else you want. Just have to figure out one thing that's true. Now, I didn't give you this. Somebody gave me this. Could they have given me this fact?
Yeah.
Sure. It doesn't matter what fact you use that's true. As long as you start with something that's true, you can figure out something else. So that's what we're going to try to figure out. So we're going to study unit circle at some point later on. We're not studying it right now. All I'm doing on the board is drawing a picture of a unit circle, which is just a fancy name for a circle with a radius of 1. Okay, so any question on what a unit circle is? Just a circle with a radius of 1. Now, there's something very special about a unit circle in terms of measuring the length of an arc and measuring the corresponding angle to that arc. This is something special that only happens on a unit circle. Does everyone understand the difference between like taking a piece of string and measuring that arc versus measuring this angle with like a protractor? They're different. Usually. But if you draw a unit circle, which is a circle with a radius of 1, if you measure the angle with a protractor in radians, and then you take a piece of string or whatever, and you measure the length of the arc, they will come out exactly the same. That only happens on a unit circle. Okay, so again, if you measure the length of the arc with a piece of string, and then you measure the angle with a protractor, the two numbers you get would be exactly the same. Exactly. Now, because they would come out the same, we can use that idea to figure out how many radians in a full circle. Because if we know the distance to go all the way around a circle, if you can figure out this, like using a piece of string, if you can tell me what that is on a unit circle, bless you, then the angle that goes all the way around is exactly the same as the arc that goes all the way around. That's what this is saying. The measure of the angle is equal to the length of the arc. The measure of the angle equals the length of the arc. So, what we basically want to do is figure out the length of the arc that goes all the way around the circle. Now, if an arc goes all the way around a circle, we don't even really call it an arc anymore because it's so big it takes up the whole circle. What do you call that?
Circle.
The what?
Circle.
Well, the circle is the physical shape. Like the color of the circle, the weight of the circle. What about the circle?
Circumference.
The circumference of the circle. If you can figure out the circumference of the circle, that's exactly the same as the number of radians to go all the way around. That's what we want to figure out. So, what is the formula for the circumference of a circle? Pi r, when you square it, that gives you an area. Yeah, because it raises it to the second power, which is like inches squared or something like that.
Pi times diameter.
Pi times diameter, or you could also say 2 pi r. Same thing. This is the arc that goes all the way around the circle. We call it a circumference, but it is an arc. Okay? It's a big arc. If you can tell me the length of that arc, it's going to be equal to the angle that goes all the way around the circle in radians. Okay, so if you tell me the length of the arc, it's equal to the angle in radians. So, what's the radius of the unit circle? 1. What's 2 pi times 1?
5.
2 pi. So the circumference of the unit circle is 2 pi. We don't know, 2 pi feet, 2 pi inches, it doesn't matter. It doesn't, not important. It's 2 pi units. So if the circumference is 2 pi, how many radians to go all the way around?
2 pi.
2 pi. Because the length of the arc, 2 pi, is equal to the angle in radians. So it's 2 pi radians to go all the way around the circle. So now we know that in one revolution, there's 2 pi radians, or 360 degrees. This is like your 1 foot equals 12 inches. It's a fact you can use to figure out anything else you want to know. But we can simplify that fact a little bit. Technically, this fact is almost like saying 2 feet equals 24 inches. You could make it a little smaller. What else could you say instead of 2 pi equals 360?
You could just say pi equals 180.
You could say pi equals 180. Now, what was the conversion somebody gave me earlier between feet and inches? What was the conversion again? 12 inches equals 1 foot. Give me a conversion between minutes and seconds. 60 seconds, 1 minute. We'll do one more. A conversion between hours and days.
24 hours in a day.
24 hours in what?
In 1 day.
1 day. So I didn't ask you guys for specific numbers. I just said, give me a conversion. That's what you gave me. All those conversions have a common theme to them. They all have a number 1. Usually when you give someone a conversion, you wouldn't say in 240 hours there's 10 days. I mean, yeah, it's true, but you simplify it, you say 24 hours 1 day. It's the simplest way to say it. Well, let's do the same thing here. Let's get a 1 in this conversion. Which side we get a 1 on is going to change if we're going from degrees to radians or radians to degrees. So I had degrees to radians first, where did it go? Right here. All right, so let's see, degrees to radians. Let's get a 1 on the, let's see. Let's get a 1 on the right side. How would I get a 1 on the right side of that equation? Yeah? Divide by 180. So now it would say pi divided by 180 equals 1 degree. So now we have a formula for 1 degree. 1 degree is pi divided by 180. Now, let's say that I wanted a formula for 2 degrees. What could I do to each side of this equation that would convert it from a formula for 1 degree into a formula for 2 degrees? I got to do the same thing on both sides. Multiply by 2. Times 2 times 2. Now I have a formula for 2. What if I wanted a formula for 5? Times 5 times 5. Okay. The pattern is anytime you want to change degrees to radians, you take the number that you want to convert, you multiply by pi, and you divide by 180. If it's 5, it's 5 times pi over 180. If it's 3, it's 3 times pi over 180. But in general, it's always multiply by pi, divide by 180. And we usually don't round pi off. There might be times where they want you to do it out as a decimal. If it's a multiple of 30 or 45, probably not. So now maybe you can start to see when we did that program on the computer where all the pi's were coming from. It has to do with the conversion between degrees and radians, which has to do with the formula for the circumference of a circle, which has pi in it. Okay, so that's degrees to radians. Multiply by pi, divide by 180. Now, let's take the same formula that we had. Pi radians equals 180 degrees. Let's get a 1 on the left. Divide by pi. Divide by pi. Pi divided by pi is 1 radian equals, and this is how much 1 radian actually is if you did it out. It's 180 divided by pi. It's about 50 something.
7.
Yeah. So 57 degrees roughly in 1 radian. Now, what if you wanted a formula to convert 3 radians? What could I multiply each side by? 3. Did the same thing on both sides, so it's still true. But the pattern to convert radians to degrees is take what you want to convert, times it by 180, and divide it by pi. So times by 180, divide by pi. Now, those are very similar. It can be very easy to mix them up. They both use pi, they both use 180. One's multiply, one's divide. If you can remember what I'm about to tell you, you don't have to memorize that. It'll just happen automatically. When you think degrees, okay, let me go back for a second. But when you think degrees, I want you to think of the number 180. Degrees, think 180. When you think radians, I want you to think pi. Radians, pi. Radians, pi. Okay. So degrees, think 180. Radians, think pi. If you remember that, all that will happen automatically. Oh, let's look at an example where we want to convert degrees to radians. Always going to multiply by a fraction. It's either pi over 180 or it's 180 over pi. Now, 30 is not a fraction, but if you wanted to make it one, what could you do?
30 over 1.
You could put it over 1. Now, we're trying to get radians. That's the end goal. Right now I have degrees. It's in the top. Where would degrees have to go to cancel out? Degrees would be in the bottom. Radians would be in the top. Now, when I said degrees, what number do you always think of? 180. Radians? Pi. So this one was pi over 180 because you want the degrees to cancel out. If you had degrees on the top times degrees on the top, it wouldn't cancel out. So, when they ask us to convert, you do not round it unless they say to. So all you can do is reduce. 30 goes into itself once. How many times does it go into 180? 6. And that's your answer. Pi over 6. Now, notice I didn't write RAD. That's because you never write RAD. I started to kind of at first just to show you. But if I could get it right on 30, you would see it is pi over 6. They don't put RAD. So then how do you know it's radians? Well, in trig, if you're talking about an angle and there's no degree symbol, it's radians. That's how you know. If you want degrees, you have to put the symbol. If you want radians, you just leave it. So if we were talking about angles and I wrote this,
School would be like, put a label on
that's
everything and then
3 radians.
no, you're
Radians don't always have pi. Okay? It depends. Sometimes the pi cancels out.
bullied in a label on every number.
But you got to get used to not seeing RAD. So from now on, RAD will be invisible. Okay. Okay, let's do 45. Where would degrees have to go to cancel out? Bottom? What number in the bottom? In the top? Remember it says RAD, so that's invisible. Degrees cancels. And now we're just reducing 45 into 180. Pi over 4. That's your answer. 45 degrees is pi over 4 radians. 60. Well,
It's just going to be pi over 4.
what's the connection between example A and example C?
Example C is just.
They go into 180 evenly.
They both go into 180. What else?
C is just double A.
It's just double. So this should be 2 pi over 6, or when you reduce, pi over 3. Once you start to know like the 30s and 45s, you could ask me what 120 is. And in my head, I say quickly, okay, 30 is pi over 6. 120 is quadruple that, so 4 pi over 6. And then I don't have to go through the conversion. But you just got to get used to the 30s and 45s first. So, might not know that yet. Divide by 180 times pi. 60 goes into 180 3 times. And pi over 3 is double pi over 6. Now, let's see if we could do 90 using the shortcut. 90 is triple A. So what would you get if you triple the answer in part A? 3 pi over 6, or pi over 2. And once you know that, you can say, oh, 270. All right, well, that's just triple. 3 pi over 2 is 270. Just triple. Now, if you ask me, like, what's 53.6 degrees, I don't know. That you need a calculator. We're going to do some round. I was going to do one with rounding, but that'll be what we finish up with. Okay, now convert to degrees. So pretend next to pi, it's invisible. RAD. So where is RAD going to go in this fraction? It's in the bottom. So pi, radians in the bottom. What goes in the top? And you've got to put the degree symbol because it's 180 degrees. What's going to happen here?
270.
Pi's cancel. Radians cancels. That's invisible. And 2 goes into 180. 90. So you're left with 3 times 90 degrees. Yeah. Which is how much? 270. Now, this one might be one if you say, okay, I remember what pi over 3 was. We just did it. This is double pi over 3.
Wait, say that again?
120.
We just figured out that pi over 3 was 60. This is pi over 3 doubled. So how much is that one? It's going to be 120. Okay. If you don't remember pi over 3, that's not going to help you. So then you just divide by pi times by 180. That's gone. 3 goes into 180. 60. And what's 2 times 60? 120. So you can still get the answer that way. It just takes a little longer. Working with angles that are multiples of 30 and 45, to me, is like for you probably doing like 3x plus 4x. You can just do it very quick. It's not that hard to do 3x plus 4x because you've practiced it a lot. Once you've practiced these a lot, it gets a lot easier. Okay, 5 pi over 4. So the way I do it in my head is I know pi over 4. It's a 45 times 5. So that's 225. That's how I do it in my head. But again, you might not know pi over 4 right away, so you just do it the long way. Divide by pi times by 180. How many times does 4 go into 180? 45. And that's exactly the calculation I did when I started. 5 times 45. Okay, so we'll finish up with one that's rounding. With rounding, the only thing that's different is you need a calculator. So, how would I convert that to radians? Times pi over 180. Now, the pi is important. Don't use 3.14 when you type it in. Use the pi symbol. Yeah. 500 times pi divided by 180. So there's nothing rounded until this step. 8.73. In general, two decimals is fine. Do I need a label on that?
No.
No, because that's radians. You don't put RAD. You don't do that. Question?
Why can't we use 3.14 pi?
I'll show you on the next one. I'll do it on this one. I'll show you why. Show you what happens. Okay, we got to get used to not seeing that. How do I convert 3 radians to degrees?
180 over pi.
180 over pi. So I'm going to do it with the pi button the first time. 3 times 180 gives me 540. Divide by pi. 171.89. Sometimes we'll do 3 decimal places, sometimes we'll do 2. 2 or 3 is fine. You do need the degree symbol, because without it, that's 171.89 radians. Now, let's do 3.14 instead. So that's the numerator, 540. Divide by 3.14. That's 171.97. If I'm looking for accuracy to the nearest hundredth, it's kind of a big difference between 89 and 97. So it throws your answer off. Okay, so any questions on that? Okay, so homework tonight, again, it jumps around a lot because we did a lot of different little things, but it's on page 323. I will put the video up right now, and hopefully it does work. If not, you can always just check out last year's. Okay. Tomorrow, don't forget, we do not have class, so this is due on Wednesday. Okay.
Cool.
Thursday's going to be a short class. not sure if we're gonna get through everything, so you may have to watch 10 minutes of a video yourself. I also might not check homework till Friday on Thursday, just to save a little time.